Let's work out a couple examples involving our new Laplace transform rule for multiplication by an exponential in t. Just to remind you of what that Laplace transform formula is, we found that the Laplace transform of some function that's been multiplied by an exponential, so e to the at times f of t, is the Laplace transform of the original function, but shifted by a, like this. I find this way of writing it a little bit clumsy. What I prefer is write Laplace transform of f, but then you replace s by s minus a when you're done. So I find this a little bit easier to use because it lets you first calculate the Laplace transform of f, and then after you're done finding that, then you do this substitution to do the shift in s. So with that in mind, let's find the Laplace transform of e to the 2t times cosine 3t. So using this Laplace transform rule, right, we have multiplication by an exponential here. So according to our Laplace transform rule, this should be the Laplace transform of cosine 3t. But then when we're done calculating that, we replace s with s minus the coefficient in the exponential, which is 2. Okay. And now we can find the Laplace transform of cosine 3t. Fortunately, we know the Laplace transform of cosine 3t. That's one that we worked out before. It's s over s squared plus 3 squared, so 9. But then remember, after we're done, we have to replace s with s minus 2. And so now we can go ahead and do that replacement, right? We've finished calculating the Laplace transform, so now we can do the substitution, or the shift. We get s minus 2 over s minus 2 squared plus 9. And we're done. So one interesting feature of this shift is it gave us an irreducible quadratic in the denominator that we couldn't have recognized as a transform before, right? Before now, the only denominator in a Laplace transform that we saw was something like s squared plus some constant squared. But right, what about all of the other irreducible quadratics? Why don't they show up as denominators in Laplace transforms? Well, they do. It just turns out that they're all shifted. That's where they all come from. So it's sort of reassuring to see that this sort of gap in the possible forms of Laplace transforms all get filled in when you just go looking for more Laplace transform rules. Let's look at a couple more examples. So how about this one, Laplace transform of e to the minus 3t times t to the 4th. So again, we have multiplication by an exponential here, so we just need to find the Laplace transform of t to the 4th, and then when we're done, replace s with s minus the coefficient in the exponential, which is minus 3. Okay, Laplace transform, so this is really going to be a plus 3 because those minuses cancel. Laplace transform of t to the 4th, that's something that we have a Laplace transform formula for. It's 4 factorial over s to the 5th. And then we need to replace s with s plus 3. So this is 4 factorial over s plus 3 to the 5th power. Here's another situation where this new Laplace transform rule has filled in a gap in the sorts of denominators we can have in our Laplace transform. Before now, we had Laplace transform rules that produce linear factors to the first power in our denominators, but now we see that higher powers just come from multiplying your exponentials by powers of t. Let's look at one more example. Let's find the inverse transform of 1 over s squared plus 4s plus 5. So this quadratic in the denominator here is irreducible. It doesn't factor. Well, you can check just by trying it out that it doesn't factor with integers. We might wonder if it factors into linear factors with irrational coefficients, but if you check the discriminant of this quadratic, right, it's 16 minus 4 times 1 times 5. This discriminant is negative, and so this quadratic doesn't have any real roots, not even irrational real roots, and so we can't factor this, right? If we could have factored this with real coefficient linear factors, we could have done partial fractions and then taken an inverse transform, but because this discriminant is negative, we can't factor this over the real numbers. But if you remember what I said a minute ago, all of the irreducible quadratics that don't factor over the real numbers, you can write them all as sums of squares if only you could figure out what goes inside of here. But there's an algebraic trick to do that. That's completing the square. So let's just complete the square here. This is the inverse transform of 1 over. So now we need to complete the square in the denominator. Let's see. So half of 4 is 2, so we need an s plus 2. And when we multiply this out, this is going to give us a plus 4, but we need plus 5, so we need one more, like this. All right, and now we see that, hey, there's a shift in the S world, and our Laplace transform rules tell us that a shift in the S world is multiplication by an exponential in the T world. So this gives us e to the minus 2t, right? So this shift in S turns into that exponential. But we still need to take the inverse transform of the function without a shift, so like this. All right, fortunately this one, I recognize that one, that's just sine. So e to the minus 2t times sine of t. And there we're done. This rule that lets us turn multiplication by exponentials in t into a shift in s, it runs backwards just like any other Laplace transform rule. So you can use it both forwards to calculate Laplace transforms and backwards to calculate inverse Laplace transforms.